Hi, this is Solideo Gloria Molecular Thermodynamics, Chapter 1, Energy Levels and Energy Levels of Atoms and Molecules, Part C, Vibrational Energy Levels. First of all, we are going to solve Schrödinger equation and need to know the potential energy. So potential surface of the molecular vibration in terms of internal coordinate, the distance in case of diatomic molecule, the bond length fluctuation, the distance between two atoms, maybe in this case, or from the deviation, displacement from the equilibrium, the most stable position. So as a function of, in terms of the displacement, well, L is the current length or current position from the reference point L0. So L minus L0 is the deviation. Let me get the pen. Yes. So L minus L0 is the deviation. So in terms of deviation, we describe the potential function. Actually, the L is the coordinate. L minus L0 is the deviation. So B of L0 is the reference point where the most stable or equilibrium position, and then the potential energy of that particular point is V of L sub 0, and then the molecular potential energy curve for that particular coordinate L is just like this one, just like that. It's ugly. So anyhow, this is the curve. So that is expanded in terms of L minus L0, which is V of L sub 0, dVdL evaluated L equal L0, L minus L0, 1/2 of d square V dL square, L minus L0 square, 1/6 the cubic derivative of dVdL and L minus L0 cube, and like that. And here, and as I said, L equal L0 is the equilibrium bond length, then dVdL equals 0, because this is the derivative at L equal L0. And then the second part, which is second derivative, is a constant here at this point. And then also third derivative is also constant, evaluated L equal L0. And then look, if we don't include any other terms except second derivative, which looks like a quadratic function, in this case dotted line here. So this quadratic function is the harmonic term. We call this as harmonic. And all others are not harmonic or anharmonic terms. So in this case, this is harmonic and all others anharmonic. And now with this L minus L0 as a deviation, we set that as X, as a deviation coordinate or replacement coordinate. So 1/2 of kx square plus 1/6 of gamma x cube, and beyond that are all anharmonic terms. So we approximate this molecular vibration as the second quadratic term only. So we call this approximation as harmonic approximation or harmonic oscillator approximation. So what we include as a potential is just this one, V of X, if one-dimensional oscillator, 1/2 of K x square. X is the displacement coordinate. Now, so this is the Schrödinger equation, just the normal Schrödinger equation, and v of x is 1/2 kx squared. So we plug this into here, and we move this to the left-hand side, and then what we obtain is this, and then because we multiply by 2 mu over h bar square minus, yeah. So, and then we have to solve this differential equation. This is Hermit differential equation. There is a known way to solve this one. That's Hermit differential equation. And then we let omega, which is k over mu of square root, and then the frequency is multiplied by 1 over 2 pi. Yeah, so that's frequency, and this angular frequency actually. Yeah, angular velocity. Then we solve this equation doing Hermit differential equation, and then we obtain the energy of the oscillator h bar square root of k over mu, and then v, actually that's v, yeah, v plus half. This v is the vibrational quantum number, or sometimes we use n instead, but v is the vibrational quantum number. And then this is the omega, this is h bar omega, and this one, and then omega is 1 over 2 pi, that. So what we get is that instead of h, we put h bar omega, we have h nu. We say is ni, Greek n, h ni. Sorry, the Greek letter is ni. This is we pronounce it ni. Anyhow, sometimes people just say nu. That's fine in English. Anyhow, okay. So h ni v plus 1/2. The ni is the vibrational quantum number, which is the 0, 1, 2, and so on. And then we obtain the wave function psi ni. The wave function is indexed by the quantum number of x, a normalization constant, and then Hermit polynomial. So this quantum number, and then e to the minus alpha x squared over 2, which is the kind of the factor, multiplication factor, to make sure that wave function converge to 0 when x goes to infinity. And then that is the, and another term is the Hermit polynomial. So this is the wave function. So we have wave function, and the given alpha, we obtain the energy just like this. So we solved Schrödinger equation for harmonic oscillator, and using the harmonic oscillator approximation, which is the v of x is 1/2 of kx squared, we solved the Schrödinger equation. Okay, so we solved the Schrödinger equation and obtained the important fruit of here is that energy is h nu and v plus 1/2. And notice that v equals 0 is the lowest energy of the harmonic oscillator, then which is not 0. We call that 0 point energy. And then among the levels, vibrational levels is v equals 0, v equals 1, v equals 2, v equals 3, like that. Among the vibrational levels, only the transition is allowed delta v equal plus minus 1. That's the selection rule that tells us allow the transition among various vibrational energy levels. And then we obtain that observable frequency of that transition is just 1, because that is equally spaced. It's equally spaced. You go that way or the other way, anywhere you go, that the distance or the difference in energy is the same. For example, and then you from the observed frequency, we can obtain the force constant. Yeah, force constants. Usually, that's the main idea, how to utilize vibrational spectroscopy of the, and then that tells us the kind of stiffness of the bond. For example, we have H35Cl, hydrogen chloride, and then this is the observed wave number for the vibration. Reciprocal centimeter is one way of expressing the energy, you know. And then K, the force constant, is here, is obtained by observed wave number times 2 pi c times mu, and then that's squared and times mu, which gives K. And then 2 pi velocity of light, and then what is this term? Is the observed wave number. And then we convert the wave number to the meter, and then reduced mass, and then AMU to kilogram conversion factor. Then we obtain that in SI unit, which is Newton per meter. So that's the 478 Newton per meter. That's the stiffness of HCl bond. So this is kind of one application or utility to use vibrational spectroscopy. Anyhow, for the diatomic molecule, we obtain energy, so that we can calculate the partition function for the diatomic molecule in this case. And also, if that's a polyatomic case, okay, before we do that, yeah, and then these are all diatomic molecules, and we have vibrational frequency and wave number, of course, that force constant and bond length, and these are all tabulated. And then, in case we need to calculate certain vibrational partition function of some molecule, for example, H35Cl or oxygen, like that, we can utilize these numbers. Basically, we use this one, this frequency, so that we can compute energy. Okay, energy. So vibrational, this is the diatomic molecule. So vibrational energy levels are equally spaced beyond 1/2 h nu, beyond 1/2 h nu, and each excited states, vibrational excited state is above h nu from the lower one. Okay, so that the transition, up transition, these all transitions are just the same, and down transition also the same. So there is only one frequency, transition frequency is observed. And now we think of polyatomic molecules. So polyatomic molecules has, for example, if you have n atoms of a molecule, n molecular atom, n atomic molecule, it's kind of different. Yeah. So if there is an atom like oxygen, HH, in this case 3-atom molecule. So in that case, each atom has a coordinate. Cartesian space 3 coordinate actually, x, y, z direction. Each atom has 3 coordinates. So in this case, 3 times 3, 9 coordinate case. So if there is n atom, there are 3 n coordinates. And so this is actually the total kinetic term Yeah, 1/2 of mv square. Yeah, so this is Vx, Vi, Vz. It's the total kinetic energy. It's just like this. And if we, this Q is a mass-weighted Cartesian coordinate. So in that case is mass-weighted, meaning is that kth atom is that the mass is mk, and then we multiply this, and then this is the difference coordinate of x and y and z direction. So anyhow, we use mass-weighted Cartesian coordinate. Then we include this into this square term. So that doesn't show up. That mass doesn't show up in the potential expression for the potential. So in that case, that is done equilibrium energy. Yeah, and then gradient. This is, we call, let me just clear this up. This is gradient. First, I mean is dient, gradient, first derivative in this case. And then this is the second derivative. In the case, the second derivative Hessian. Then, and so on. So notice that the gradient is just as a function of one coordinate, and Hessian as a function of two coordinates. But somehow we diagonalize this so that there is no cross term. That resultant coordinate, of course, that Hessian doesn't have a cross, meaning is that off diagonal element. So no cross term, we call that normal coordinate. Because there is no cross term, we can decompose it as an independent vibration. So in that case, that is done, which is this new coordinate which doesn't have a cross term. What I mean by that is that K, you see here, for example, II is only, no ij terms here. So QI, like that. Okay, then all are just the diagonal terms. The other, no off diagonal terms here. So that we call as a normal coordinate. That is the capital Q here. If that's normal coordinate, and then if there are n normal coordinate, we can treat it n separate or independent harmonic oscillators. That's the beauty of it. And how many vibrations are there? If there are n atom molecule, then there are 3n coordinate. Out of 3n, there must be 3 center of mass coordinate, which is the kind of mass center. And then rotational coordinate. This is, if the center of mass moves, then that's a translation. So we call this as translational coordinate or translational degrees of freedom. Degrees freedom. Okay, degrees of freedom. And so if there are 3n n atoms molecule, then 3n coordinates are there, and 3 are translational. And if that's linear molecule, then there are 2 rotational coordinates. Non-linear, general molecule, there are 3 rotational coordinates. For example, if this is a linear molecule, and then if you rotate this way, there is no torque, meaning is that there is no angular torque here, so it doesn't count for the degree of freedom. Only what is cross, right angle to that molecular axis, and this way and this way. These two rotation counts the torque. So linear molecule has only 2 rotational degrees of freedom. Non-linear molecule has 3 degrees of freedom, rotational. So vibrational case, 3n minus 5, 3n minus 6 degrees of freedom are vibrational. 3n minus 6 degrees of freedom are vibrational. So which means that many 3n minus 5 for the linear, 3n minus 6 for the non-linear molecule, then many normal coordinates are there. Meaning is that many frequencies you can obtain. So 3n minus 6 is in general non-linear case, and then what I just mentioned that in normal coordinate system you have that many vibrations, or you can decompose the total Hamiltonian into separate that many 3n minus 6 Hermit differential equation. So when you solve each one, well, actually you solved already the Hermit differential equation, and then total wave function is that each vibrational wave function product of each vibrational wave function, and then total energy, vibrational energy, is the sum of those normal coordinate, energy of the normal coordinates. So the displacement of motion of the normal coordinate does not change the center of mass, does not rotate the molecule. So it must be shown just like that. If you analyze normal coordinate, you will see its motion. Actually, that is done. Well, when you do quantum chemical calculation using Gaussian program as such, then you may utilize more than. We did that in some way. We did that in some classes. And visualize this normal motion, normal coordinate motion. Okay, I just stopped it somehow. Back. So it shows that well, actually, this is a 3-atom molecule. For example, close to water. Yeah, this is water. Symmetric stretch. It does not move its center of mass, nor it does not rotate the molecule. And asymmetric stretch, also it does not move center of mass, probably somewhere here. And then, did you see that? Actually, it doesn't show. Yeah, somewhere here. Yeah. And then bending, symmetric bending. These are normal vibration. The other 3 under it are libration. It's not really vibration. It's a kind of rocking motion within some kind of cage of other molecules. So I covered mostly about vibrational energy levels of molecule. So you solve vibrational Hamiltonian Schrödinger equation, which is the Hermit differential equation. You obtain vibrational energy. Electronic energy is a lot bigger. Vibrational energy is matching kind of smaller than that. Rotational energy is much smaller, which is the next topic. So let me end here for this section, and then we'll have the last section in a moment.